Let's jump right into this explainer. We've covered a ton of theoretical ground so far, but right now, no new theory today. We are taking every single formula from this chapter and using them exactly the way you'll actually use them in the real world, sizing a real magnetic circuit.
The crucial thing to remember here is that you already know how to solve this. Seriously, if you can solve a basic electrical circuit, you can solve a magnetic one. It's the exact same math, we're just mapping it to different letters. So, in an electric circuit, voltage pushes current through a resistance. Well, in a magnetic circuit, magnetomotive force, or MMF, pushes magnetic flux through a reluctance. It is literally the exact same underlying logic. And that brings us to reluctance, which is, you guessed it, simply the magnetic equivalent of resistance. Just like electrical resistance limits how much current flows through a wire, magnetic reluctance dictates the opposition to magnetic flux. It depends entirely on your course geometry and the material's permeability. So a low reluctance material, like a nice solid steel core, allows magnetic fields to flow almost for free, just like a thick copper wire does for electricity.
Now, for a magnetic circuit in series, say a steel path and then a deliberate air gap, the total reluctance just adds up exactly like series resistors. Your total reluctance, R total, is just the reluctance of the core plus the reluctance of the gap. Simple as that.
But here's the crazy engineering reality about this. Air is absolutely terrible at conducting magnetic fields compared to steel. We're talking thousands of times lower permeability. Because of that massive difference, even a tiny air gap, literally a millimeter or two, will completely dominate the total reluctance of the whole path. That is exactly why air gaps matter so much in relay and actuator design. Okay, so what about parallel paths? Think of a standard three-legged transformer core where the flux travels up the center and splits between two outer legs. Those reluctances combine exactly like parallel resistors. 1 over R total equals 1 over R1 plus 1 over R2. The magnetic flux always takes the path of least reluctance, splitting inversely to each leg's resistance to flux, exactly like electrical current does.
Let's do a quick check to make sure this is locking in. Imagine you have two parallel magnetic legs in a core. One leg has exactly half the reluctance of the other. Which one is going to carry more of the magnetic flux?
If you said the lower reluctance leg, you are absolutely right. By the parallel splitting rule, it'll carry roughly twice as much flux as the other leg. Why? Because flux is fundamentally lazy. Just like current, it will always favor the easier path. Let's look at a real example and build this step by step. Imagine you're designing a relay, and you need exactly 0.8 milliwebers of flux through a core. After checking your dimensions, you find the total reluctance is 500,000 ampere turns per Weber. So how much current do you actually need to supply to make this work? We just use the magnetic version of Ohm's law. Your required MMS is simply your flux times your reluctance. So 0.8 milliwebers times 500,000 gives us a required driving force of 400 ampere turns. That's the total magnetic pressure we need to generate. And since MMF is just the number of turns on your coil multiplied by the current flowing through it, finding our amps is super easy. Divide our 400 ampere turns by, say, a standard 150-turn coil, and boom, we need about 2.7 amps of coil current to successfully drive this relay. But wait, sizing the steady-state current is really only half the battle. A static magnetic field just sitting there perfectly still inside a coil doesn't actually induce any voltage. For voltage, we have to look at Faraday's law, which tells us that an electromotive force, or EMF, is only induced when that magnetic flux changes or collapses. It is all about dynamic movement. Let's apply this back to our relay. What happens when you suddenly switch it off? You cut that 2.7 amps, and our 0.8 milliwebers of flux rapidly collapses back to zero. Let's say this collapse takes just 5 milliseconds. To find the average induced voltage, E average equals N times delta phi over delta T. That's 150 turns times 0.8 milliwebers divided by 0.005 seconds. Run those numbers and you get about 24 volts. That rapid collapse generates a 24-volt spike across the coil. This isn't just fun math trivia. That spike is exactly what a snubber or flyback diode on that relay needs to be designed to safely absorb and survive, so you don't blow out your switches. And just like that, you've got the complete toolkit. You came into this explainer with electric circuit theory and nothing else. You are leaving fully able to build and solve series and parallel magnetic circuits, size the MMF for a target flux, and calculate the induced voltage from a flux change. This is the exact foundation every transformer and machine chapter from here on out assumes you already have. So, the foundations are officially set. But I want to leave you with this thought. If these straightforward formulas can perfectly predict the behavior of a tiny little relay, how incredible will it be to see them scale up? Next up, we are going to build the massive multi-ton machine that runs our entire electrical grid on these exact principles, the power transformer.